Hello students. In the previous section we have discussed about the Legendre and Hermite polynomial. Now we will shift to the unit 3. In unit 3 the first section tells about the simple recurrence relations regarding Legendre and Hermite. We have already discussed about the recurrence relation, but you should go through these relations and its small derivation once. I've already provided the PDF in the description box below, and also the same will be shared in the group. Now the next part will be the expansion of an arbitrary function in a series of Legendre polynomials. Okay, so as you see, we need two functions for that. First is your phi n x, later is our x. So we have to consider the function phi n x to be a complete orthogonal set in a particular interval a to b. And as we know, what is the definition of orthogonal? As you see from the property, it is generally a non-zero vector set or any kind of set in which, suppose there is a set of u1, u2 up to un. Suppose that is set. The AB can also be expanded like this form. So if ui dot uj will be equal to 0 for I is not equal to 0, then that set is called as a orthogonal set. Okay, similarly if there is any kind of a, suppose ai dot aj is equal to 0 for I is not equal to 0, or bi dot bj is not equal to 0 for I is not equal to 0, then this function in the interval AB is called as orthogonal set. And when it becomes complete, when A and B also becomes orthogonal to each other, means AI dot BJ is equal to 0 for I is not equal to 0. So they form complete orthogonal set upon this AB. Now comes to the function, that is f of x. So we have to consider this function and also its derivative. You have to consider the function and also derivatives must be sectionally continuous. Sectionally continuous. What does that mean? Sectionally continuous means we know that it is continuous in the interval AB. Sectionally continuous means we have to divide this interval into number of subintervals. Number of subintervals, like suppose A1, A3, A4, A6, like on B1, B3, like Bn-3, Bn, like that. Okay, we will divide into different subinterval, and this function and its derivative will be finite and continuous in both these intervals or in all these intervals. I am repeating again, the function f of x and its derivative is said to be sectionally continuous when it is continuous at all these subintervals, and also this function have a finite value in all these subinterval. They are called sectionally continuous. So in the expansion property, you have to consider first function, that is phi n x, to form a complete orthogonal set. Another function f of x, which along with the derivative will be sectionally continuous in the interval AB. So at that time the function f of x can be expressed as a linear combination of orthogonal basic functions. So now it can be expressed as a linear combination of orthogonal basic function. So it is represented as summation over n is equal to 0 to infinity a and phi n into x. Here a and are the coefficients or constant, you can say. It is the constant coefficients of the linear combination. Okay, this is the basic fundamental of the expansion. Now we'll straightforward move to the derivation part. So we know from the orthogonal property, as we have studied from the Legendre polynomial in the interval a b, we can write from a to b phi n x phi mx dx will be is equal to c into delta mn. Okay, so as you can see, there are two interval from a to b, function phi n, which is an orthogonal function. Similarly, the similar kind of function, that is phi mx, is also orthogonal. When you take the integration, you will give rise to a constant with the Kronecker delta property. And we know by virtue of the Kronecker delta property, it becomes c into 1 when m is equal to n. It becomes 0 when m is not equal to n. I hope every one of you have know this. Now the main theme here is to derive the coefficients. Okay, we have to derive the coefficient here. So what kind of coefficient we have to derive? We can derive the coefficient am. So now to evaluate the coefficient am, you can write her an. Okay, you write her ap, aq, ar, whatever you can say, because it can take any value. It's a variable one. Okay, we have to evaluate now the coefficient am. So what we have to do? Suppose we take it as equation 1, suppose we take it as equation 2. What we have to do? We have to multiply this am in both sides of equation 1. Okay, and then we have to integrate it from interval a to b. Okay, so you have to multiply am on both the side of the equation 1, then you have to integrate it with respect to x from interval a to b. So equation 1 becomes a to b f of x phi m x, sorry, it's not phi am, this is phi m, sorry, phi m of x dx is equal to summation over n is equal to 0 to infinity. An is a constant coefficient, so we can take it out. An integration over a to b, again it is phi nx, and we have multiplied what? Phi m, it is phi m dx. Okay, so in order to find out the constant coefficient an or am or ap, whatever it will be, we have to multiply what? We have to multiply phi of m on both sides of the equation 1 and then integrate it. So now after integration, what we will get? We will get summation over n is equal to 0 to infinity an. Okay, you can see these things, that from the orthogonal property, this equation will reduce to what? C into delta mn. So it becomes C into delta m into n. Okay, so now the pictures came whenever an coefficient is operated with an Kronecker delta function, then similar function reduces and the non-similar function remain there. Like for example, suppose it is b and delta mn. Okay, so it will be, when operated, we will give rise to what? It will give rise to your bm. Okay, therefore whenever the coefficient an will be operated over delta mn, so we will get what? We will get summation over n is equal to 0 to infinity c into a m. Okay, so the coefficient when operated over the Kronecker delta function, the similar indices reduces and the dissimilar one remain there. So integration over a to b f of x phi m dx will be equal to summation over n is equal to 0 to infinity c into a. Okay, let it be equation number 3. Okay, now we have seen the function of am and also the function of phi n here. So as this property satisfied by an orthogonal set function, we have to see whether this function is satisfied Legendre polynomial or not. Okay, so Legendre polynomial from its basic definition lies in a particular definite interval. Okay, the persons or your student whoever have seen the graph, I hope every of you have showed the graph of p and x. As you can see, it's a graph. I'm just taking the rough one. There's a p, okay, there's a p and x. So generally whenever the graph is plotted, like whatever may be the graph, okay, for graph tree, it generally lies between a section of +1 to -1. It's just a particular graph. Okay, so it has a definite value, and also this Legendre polynomial forms a complete orthogonal function. So we can replace the phi n with respect to the Legendre polynomial. Okay, I am summing my argument. Look, the Legendre polynomial represented by p and x. Okay, they form complete orthogonal set. By their property or by their definition, they form complete orthogonal set. They have a definite value. They lie between +1 to -1. Okay, so you can see from the definition. देखो तो पहले आमे तले एक्सप्रेशन बाहर करथिला एक्सपांशन रो म का नथिला phi n टा गोटे कंप्लीट ऑर्थोगोनल सेट हबा आतर कना डेफिनेट वैल्यू रहबा जेतु सेटा सेक्शनली कंटीन्यूअस हबा तो डेफिनेट वैल्यू रहबा तो ई सेम प्रॉपर्टी जहाँ जहाँ phi n रहबार कथा लेजेंडरी पोलिनोमियल भी से समान प्रॉपर्टी सैटिस्फाई करूछि सो we can rewrite equation 1 as f of x is equal to summation over n is equal to 0 to infinity a n p n x. ଯେତେବେଳେ ଆମେ phi n x ଲେଖିଥିଲା ବେଲେ ଆମେ ନେଇଥିଲା ଯେ ସେଟା ଗୋଟେ କମ୍ପ୍ଲିଟ୍ ଅର୍ଥୋଗୋନାଲ ସେଟ୍ ହବା ପ୍ଲସ୍ ସେଟା କାଣା ଗୋଟେ ଡେଫିନାଇଟ୍ ଭ୍ୟାଲ୍ୟୁ ରହିବା ବିକଜ ସେକ୍ସନାଲି କଣ୍ଟିନ୍ୟୁଅସ୍ ହେଲେ ସବୁବେଳେ ଡେଫିନାଇଟ୍ ଭ୍ୟାଲ୍ୟୁ ରହିସି ଯେତେବେଳେ ଆମେ ପ୍ରପର୍ଟି ଅଫ୍ ଲେଜେଣ୍ଡରୀ ପୋଲିନୋମିଆଲ ଷ୍ଟଡି କଲି ଆମେ ଦେଖିଲେ ତାର ଗ୍ରାଫରୁ ଯେ ସେଟା ସବୁବେଳେ -1 ରୁ +1 ଭିତରେ ହିଁ ରହିବା ଆଉ ସେଟା ଗୋଟେ କମ୍ପ୍ଲିଟ୍ ଅର୍ଥୋଗୋନାଲ ସେଟ୍ ସବୁବେଳେ ଫର୍ମେସନ୍ करबा ସେଥିଲାଗି ଆମେ ଇକ୍वेସନ୍ 1 के रिप्लेस कर पारमा लेजेंडरी पॉलिनोमियल संगे लिखि पारमा f of x is equal to summation over n is equal to 0 to infinity a n p n x. Okay, a n p n x. Okay, so now we can take the same procedure what we have done with respect to our first equation. मन का करबा फिर से कोएफिशिएंट am टा बाहर करबा हमें ट्राई करबा. So now to evaluate the coefficient am for equation 4 जे समान प्रोसीजर फॉलो करबा काना करथिला हमें से जगह रे दुई साइड phi m मल्टीप्लाई करथिला हला ए जार काना मल्टीप्लाई करम यार pm मल्टीप्लाई करम सो मल्टीप्लाइंग pmx on both side of equation 4 and integrate and then integrate. What will you get? We will get f of x into pmx dx -1 to +1 कारण के हमर इंटरवल के -1 +1 अछि एक मिनट में ग्राफ देखे देसी मतलब कोन मे भी बुझि पारबो वेट अ सेक maybe I can show you the graph if possible. Where is that graph? Yeah, as you can see from the picture, I hope now you can clear from these things. As you can see from the picture here, okay, so the p of x. Okay, p of x, let's see, it's different Legendre polynomials for different graph. Okay, it is continued. It is only for p0, p1, p2, p3, but there are various up to n number intervals. So whatever may be the polynomial, when you draw the picture, its final limit will be must between -1 to +1 along the y, and also -1 to +1 along the x. Okay, so all the linear polynomials are concentrated or confined into this finite limit. It's also provided in the PDF also. Okay, therefore you have to take the -1 to +1 interval. So again it will be -1 to +1 summation over n is equal to 0 to infinity an pnx into pmx into dx. So obviously c is a constant, an is a constant, so you have to take it out. So it will be an summation over n is equal to 0 to infinity. Now we'll apply the same orthogonal property -1 to 1 pnx into pmx dx. तो केते ही जा पहिले केते ही जा मन पडुछ किछि आ प्रीवियस दिन बाहर करथिला. ओके, फ्रॉम प्रीवियस लेजेंडरी ऑर्थोगोनल प्रॉपर्टी जिन माने पढिछ सन मन रहितबा आमे लिखिथिला -1 to +1 pnx pmx dx is equal to 2 divided by 2n plus 1 delta mn. इटा बाहर थिला पहिले जेतला प्रीवियस क्लास रे और क्लास रे डिराइव कराइथिला. So now also this part of the equation will reduces to 2 divided by 2n plus 1 into delta mn. Okay, देखो पहिले ई टर्म ता कांस्टेंट अछि. ओके, ई टर्म ता कांस्टेंट अछि. तो हम ई टर्म टा हम ई तरफ ऑपरेट करमा. ई टर्म टा ई तरफ ऑपरेट करमा. देखो पहिले इटा काना हे जेबा, इटा हे जेबा summation over, okay, n is equal to 0 to infinity मेरे यार के धरिया से 2n plus 1 an delta mn. So now this equation can be reduced to a n del, sorry, there's a mistake, look, 2 plus an. Okay, so this will be written as -1 to +1 f of x pmx dx will be equal to summation over n is equal to 0 to infinity 2 by 2n plus 1 an into delta mn. Okay, so मैं कहते जितने आम an ऑपरेटर के सॉरी an के आम डेल्टा ऑपरेट करमा तो कौन होगा सेम इंडिसेस रिड्यूस हो जावा और वैनिश हो जावा और डिसिमिलर इंडिसेसटा खाली रहबा. So it will give rise to am. Okay, and we will follow the same term for this also. Why? Because n is a variable one. We can replace this at any instant of time with our sum mode of convergence. So it will be 2 divided by 2m plus 1. Okay, n is a variable, and as per the control delta function, it can be reduced to the property delta m. तो हमने लिखि पारबो directly from the property of deduct delta, from the deduct delta लिखि पारो कि chronicle delta property लिखि पारो. chronicle delta property deduct delta property direct लिखि पारो. So हम काना पामा ई जगह रे तो हम वर्तमान पामा am now can be written as 2m plus 1 divided by 2 minus 1 2 plus 1 f of x pmx into dx. ये हमर हला बाकी डट के बोलाले इटा हला 2m plus 1 हला m बाहर गला हमर इक्वेशन टा बाहर गला. तो हम an भी जान रखि पारबो ई जगह रे यदि हम n के कॉन्फिडेंस कर जाउछो से समानटा ही हवा 2n plus 1 by 2 minus 1 to plus 1 f of x खाली भीतरटा pn लिखबो. पहिले m और n कंफ्यूज नहीं हवा बिकॉज़ m जारे तो p लिखि पारो q लिखि पारो s लिखि जहा भी ये वेरिएबल है खाली फॉर्मेट टा ई हिसाब रे तमर रह. ओके, तो देखो हमर am बाहर गला और an बाहर छी. यदि वर्तमान an के हम के सब्स्टिट्यूट करबा पहिले इक्वेशन 4 रे हम सब्स्टिट्यूट करबा. तो इक्वेशन 4 रे सब्स्टिट्यूट करले हम काना पाबा नाउ substituting this in equation 4. Equation 4 and substitute karma ame kana paima f of x will be is equal to summation over n is equal to 0 to infinity 2n plus 1 by 2, okay, integration over minus 1 to plus 1 f of x pn x into dx pn x into dx এটা কোন an ର ভ্যালু না এটা আমি লাগে ব্র্যাকেট করে পারো কেন লিখি পারো, ওকে, ইনটু লাস্টে কানা আছে লাস্টে আছে আমার pn x লাস্টে আছে আমার pn x ହେଲା suppose এটা নাম আমি ইকুয়েশন 5 নেবা 6 নেবা না যাবে নেবা সো an ର ভ্যালু পাই গলা আমি এতকি ଆଉ pn এটা হলো টোটাল আমার f of x in an expansion format. Now we have to do the direct application. How can we apply this in a stretching form, or how can we stretch this value for different Legendre polynomials? Those who have worked out the Legendre polynomials, they have to know the values for different polynomials. The value for different Legendre polynomials can be written as, तो मन रखा पे एटलिस्ट 2-3टा वैल्यू माने p0 p1 p2 एटलिस्ट ई केतरा वैल्यू मन रखो ना सुविधा हवा तुमको ना ट्राई करो मन रखवा लागि तो जनरली हमर p0 र वैल्यू हमर रॉड्रिक्स फार्मूला रे भी कैलकुलेट करि परबो तमे एटा हवा ऐसे 1 p1 टा ऐसे x p2 टा ऐसे हाफ 3x² - 1 p3 टा ऐसे 1/5 5x cube minus 3x है तापर कंटीन्यूअस तुम एटलिस्ट 2-3टा वैल्यू मन रखबो जेंटा कि तुमको एक्सपांड करबारे सुविधा हो, okay. So now we can express any function of x in terms of Legendre polynomial. वर्तमान so now we can express any function of x in terms of Legendre polynomial, okay. Suppose we are taking some example. Suppose we have to expand x square as a series of Legendre polynomial, okay. We have to express or expand x square as in the form of Legendre polynomial. So what is the degree of x square? It is 2. The degree is 2. So we can write f of x is equal to x square is equals to summation over n is equal to 0 to infinity a n pn x. So what we can write? We can write a0 p1x plus a1 p1x plus a2 p2x, okay. a1 sorry it is 0, sorry, a0 p0x a1 p1x plus a2 p2x. Now we have already know this value from p0x, it is p1x, what is p2x. We have to find out a0 a1 a2. How? We have to apply this formula. Now so now substituting for n is equal to 0 1 2 we have to get the respective an value. What will we get? We will get a0, so n is equal to 0, soon 1/2 is half integration over -1 to +1 -1 to +1. Now it is f of x into pnx. f of x केते अछि x square, n टा केते 0 अछि त हम लिखमा x square into p0x into dx is equal to half integration over -1 to +1 x square and p0x केते पाइछु 1 पाइछु 1 into dx. तो हमें कना हाफ टा खाली x square इंटीग्रेशन हवा तो এটা केते हेबा x cube by 3 limit is from -1 to +1. तो जब सॉल्व करले पाखा भी पाबो 1/3, okay. ये पाबो 1/3 सिमिलर हम a2 बाहर करमा सॉरी a1 बाहर करमा a1 इज इक्वल टू केते 2n + 1/2 तो 2 के 2 + 1 3/2 ओके अगेन इंटीग्रेशन ओवर -1 to +1 f of x केते x²। अच्छा p1x का केते पामा x into dx तो इटा हे जबा 3/2 -1 to +1 x³ into dx तो इटा केते हे जबा 3/2 x और f जानि छ ओके +1 सो इटा बुझाय केते फॉर्मूला बाहर 0 इधर सॉल्व कला पर इटा बाहर 0 सिमिलरली a2 मैं डायरेक्ट लिखि दे वैल्यू माने तुम डिराइव करो के लिए इट्स पाखा पाखे बाहर 2/3 ओके तो a0 पहला मैं कहते 1/3 पहला a1 पहला 0 और a2 पहला 2/3 बर्तमान सब के हमें केने पुट करमा ये सब के हमें पुट करमा ई जगह रे ये इक्वेशन 6 रे हमें ई सब वैल्यू के पुट करमा a0 पुट करमा a1 तो 0 बाहर हिचे तो टर्मटा 0 हो जा पूरा खाली a0 और ई टर्मटा आसबा तो हमें लिखमा f of x माने x² इज इक्वल टू मैं लिखि पारमा f of x जेंटा के हम x² नेचू इज इक्वल टू a0 पाइ छु केते 1/3 हला p0 पहला 1 प्लस इटा 0 अच्छे a2 पर टोटल टा 0 है a2 पहला 2/3 अच्छा p2 केते पाइ छु p2 हम पाइ छु हाफ 3x² - 1 so we can write half 3x² - 1 ओके तो हम एथे लिखि पारमा केते हम एथे लिखि पारमा इट इज 1/3 ओके ये सॉल्व करि न कर पारबो 1/3 प्लस ओके 1/3 प्लस द p0x sorry students I think there is a mistake you can substitute like this let's simplify it sorry students there's a mistake so as you have derived a0 a1 and a2 now you have to substitute all this so we can write f of x is equal to x² it is a0 p0x plus a1 p1x plus a2 p2x so a0 we have already get 1/3 p0x this term is a1 is 0 so it is 0 finally a2 is we have get 2/3 so it is 2/3 okay it is 2/3 p2x or p2 okay so this is the expression so finally we can derive the polynomial with respect to the orthogonal property x² is equal to 1/3 p0x you can neglect the 0 p0x plus 2/3 p2x okay some students may ask or I also done the same mistake here as I have substitute things but when you substitute this p0 value it will reduces to further to a simplified function x² value okay so this is not our aim okay and there is another reason that whenever we have to conclude the p0 value and p2x okay so it generally depends what are the divergence term divergence property okay so we can't directly substitute whatever we get for the nth value okay so you have to retain this term we only apply this p0 and p2 value when we are evaluating the a0 okay whenever we are evaluating a0 the constant coefficients then we have to apply this p0 value not in case of the final proceeding because in the final proceeding we have to think what are the convergence property it takes because if the convergence appears then there might change the terminology because if this term converges to x² then we can neglect this term if this term converges to x then we can neglect this term okay so for that reason we cannot directly substitute p0 or p2x. Okay, I hope it is clear to you all. Okay, so there is an alternate method. Okay, there is an alternate method where we also find the same procedure or same thing. Okay, how? Let us think. So what is the alternate method? Okay, many books like your H.K. Das have also prescribed this method. So I have substituting, I have writing this term also. Suppose we are taking x square. We have already expand this in terms of a1 p1x plus a2 p2x. So now first we don't substitute a0 a1 a2, rather we substitute p. Okay, in the previous procedure we substitute we first evaluate a1 a0 a1 a2 then substitute, but here in this procedure we have to substitute direct the value of p1 p2, okay, or p0, not the value of a0 a1 a2, and also we are getting answer. Let's see. So a0, the p0 value is 1, a1, the p1x value is x, a2, the p2x value is 1 by 2 3x square minus 1. So when we simply see the expansion, we can see that this term and the first term of this thing contains x. This term and this term are simple integer expression. So we just take this term and this last term into one picture. So we can write a0 minus half a0, sorry, half a2, I think, a0 minus half a2, and the remainings are here a1x plus 3 by 2 e2 x square. Now what we do, we have to compare the coefficients. Now we have to compare the coefficients of different power on both sides. You have to compare the coefficients of different power on both sides. Okay, when you compare this coefficient, we can see that here x to the power is 0. Okay, or we can write 0 into 0 0 plus we can write what? The secondly we can write the term remaining, that is x square. Now compare the coefficients, you can see easily that the coefficients of this term is 0. Okay, also there is no term for x to the power 1. Okay, we can write, so there is no term for x to the power 1 also, so therefore the coefficient of a1 also tends to 0. But you can see there is a coefficient for a2. Okay, because x square coefficient 3 by 2 a2, also there is a 1 multiplied across the term x2, so we can compare. So what we do, we can compare coefficients. We can compare coefficients of different powers on both sides. So what we will get? We can see a0 minus half a2 is equal to 0. a1 is also is equal to 0, but 3 by 2 a2 is equals to 1. Okay, so from this what we will get? We will get a2 is equal to 2 by 3. We have already got a1 is equal to 0. Now we can easily get from here that a0 value is equal to what? Half a2 2 by 3, so it is 1 by 3. So we got a0 1 by 3, a1 is equal to 0, a2 is equal to 2 by 3. So we can now substitute this value here, all this value here. So finally we will get x square is equal to a1 is 1 by 3 p0 x plus, as a1 is 0, so already this term vanishes out, a2 is 2 by 3 p2x. Hope you can see the similarity here. Okay, in both the procedure we find out the expansion of any term, any x term or any related term with respect to the Legendre polynomials. I hope it is understandable to you, as it is the initial class, so that it might face some error. Any doubt, you can leave a comment or you can directly message me. This is for today, students. Thank you.